Okay, well, you know, when I visualize this as a paraboloid, I totally screwed up. Okay, it's not a paraboloid. You move that 2xy there, you got a paraboloid, but the 2xy does just rotate the circle. Bonehead me. Okay, so this direction field is totally not right for this function. Now, in a minute, I'm going to change this function, then pretend that I'd never made a mistake. Okay? But let's continue with this actual function. Okay? Here's your gradient. The I component is always equal to the J component, as I said when I did that in my head. Just wanted to write it out and make sure, but that's it. Interconvertibly, I screwed up. Gradient field is always this. Now, it gets bigger or smaller depending on what x and y are. Okay? You know, the bigger x is, and you know, the bigger the sum of x and y, the bigger the gradient, right? But the direction of the gradient is always at 45 degrees with respect to the x-axis, because the I component and the J component are always equal. Okay? So this leads to a picture like this. Now, having drawn it a little more accurately, where you have the negative 2/5 slope, okay? So I'm saying that's, if that's 2, that's 5, so that's about the right slope, okay? And that's not really 2, because that's like 4/5, and this is 2, okay? It's very clear from the picture, it looks from the picture like the gradient is never perpendicular to the line, right? It looks like the gradient is always has a component in the left to right direction along that line. Okay? And of course we can easily prove that because we know that what the slope of the line is, and the negative reciprocal of that slope will be 5/2, right? And the slope of this is 1. So we could actually just calculate the angles, arctangent of 5/2 and arctangent of 1. Okay? Arctangent of 1 being your 45 degrees. Okay, well, we can do all that. But what does this tell us that's relevant to the whole idea of maximizing a function along a constraint curve? What it tells us is that for this function, the gradient always has a component in this direction, right? So if we draw this thing, the gradient always has 2 components. I'll just kind of depict those components for a couple of the vectors, and we won't draw as many. But if you find the components of the gradient, you always find that there's a component in this direction. Well, the gradient is the direction of maximum increase, okay? And the direction of maximum increase has a component along this direction of the curve, same component along this direction of the curve, right? So this is your direction of maximum increase. This is a component of your direction of maximum increase, meaning that the function is increasing as you move along this curve in this direction. Okay? Now you can reconcile that, and you should, with the directional derivative. In other words, you take a vector in this direction, okay? And what's a vector in this direction? Well, 5i minus 2j. And dot that with any vector in this direction, you find that you get a positive result. And that also shows you that the function is increasing as you move in this direction. Okay? Now you might want to come back and look at what I just said after you've worked a little more with the directional derivative, although presumably you've done some now, but it's, yeah, maybe hasn't sunk in completely. Okay, so this shows us on the curve or on the line, function's increasing as we go from left to right, right? So here we have direction of maximum increase. So in any direction that has a positive component in this direction, a component, where the I don't even want to, where the projection doesn't go backwards, where this thing makes less than a 90-degree angle. Any direction that makes less than a 90-degree angle with this thing, the function's going to be increasing. Okay? Now, if the function actually looked like this, and it will in a minute when I erase that 2xy, okay? If the function actually, if the gradients actually did this, then you would have places where, as you move in this direction, the function is decreasing up to here. Okay? Because the component of your gradient in the direction of motion is opposite to your direction of motion. Okay? Does that make sense? And then from here to here, the gradient has a component that is in this direction. So the gradient has a component opposite motion left to right along the curve, then a motion positive left to right. Meaning that the function would be decreasing from here to here and increasing from here to here, and there would be a minimum. Okay? So does that make sense? That's your basic geometric intuition. You're given a formula that any fool can apply, okay? But it embodies a situation that has some fairly deep complexity, okay? And we haven't quite gotten to the bottom of that, but that's the idea, okay? Now how do those formulas you have embody this idea? That's what we want to try to get at.